I am Anil Kumar. In this video, we'll discuss basic concepts of pairwise independent events probability. The question here is, if A and B are independent events, then prove that A and complement of B are independent, B is complement of A, and B are independent, and complement of both these events are also independent, right? So we are trying to prove that if A and B are independent, so when we say A and B are independent, it means what? When we say A and B are independent events, it means what? It basically means that the probability of A and B is equal to probability of A times probability of B. That is what it means. Now, if you have to prove all these things, that their complements are also implement, or the combination with complements is implement, then we have to basically prove, if I do A complement B, then should be product of probability of A complement times probability of B. That is the whole concept, right? So let's try to understand with the help of a diagram. So let us say this is the sample space we are talking about. Now, in this sample space, we have two events. A and B. So if these are the events A and B, in that case, the space here is intersection of event A and B, correct? How about this area where we have A but not B, right? So this area here is A but not B. Do you see that? So what I'm trying to say here is that the area, which is kind of this area, is A but not B. On the other hand, you will notice that we have this particular area which is B but not A. Is that clear? This area is not A but intersection of B. So these are the three cases which we are looking for. Do you get an idea, right? So the cases which we are looking for are A, which is intersection of A and not B, and then we are looking for the case which is intersection of not A and B. The third one here is not A and not B. That means what? That means what? Not A and not B. Well, this is the outside area. So this area here is intersection of not A. There is A is this much, right? Not A is all outside and not B. Do you see that? So this is not A, not B. The whole space is not A, not B. So I hope you have understood the question, right? So what you have to prove here is, for A, you have to show that the probability of A intersection not B is equals to probability of A times probability of not B. And for B, you have to show that probability of not A and B, they are independent if and only if the probability of not A and B is probability of not A times probability of B. And for C, in this particular case, you have to prove that the probability of these events, complement events intersection, is basically equals to probability of A times probability of B, right? Complement. That is what you have to prove, right? So once the concept is clear, I think you can now pause the video, prove it yourself, and then look into my suggestions, right? So let's see one by one all the three scenarios. So now let me take up the first case where we are given, so I'll make a smaller diagram here. So let's say that is our sample space, where we're looking for A and B are independent events. So let's write down, that means probability of A intersection B is equals to probability of A times probability of B, right? We need to prove that probability of A not B is equals to probability of A times probability of not B, correct? That is what we have to prove. So let me again draw the same diagrams, which is one circle which is of A, this is A for us. The other circle will keep the same colors. It will help us to, just understand our concepts. B, so that is our circle B. Now when we say A not B, we are looking into this area, correct? We are looking into this area. A but not B. Is that clear? We are looking into this area, which is A and not B. Now you will notice that the center portion here, which, let me use another color here, this area is A intersection B. So if I add, this is like A intersection not B, and this is A intersection B, correct? That's the intersection of both A and B. So from here you can very clearly see that the combination of these, that means A intersection not B plus A intersection B, is actually equal to A, right? Is the whole A. Perfect. So therefore the probability of A complement B could be written as, let's rearrange this, could be written as probability of A take away probability of A intersection B, right? So I hope this step is clear, right? So what we did was, we took the probability here. Now since we know it's an independent event, right? And we moved this on this side, correct? It is an independent event, so we'll now write the probability as product of probability of A and B, right? So we could write this as probability of A minus probability of A times probability of B. You could take probability of A common, which gives you 1 minus probability of B. Now what is probability of 1 minus probability of B? It is probability of complement of B. Is it okay? So you get the required result, which is as we wanted. Probability of A intersection with not B is probability of A times probability of complement of B. Since that is true, we can say that the events A and B are, so therefore we can say the events, let me write events, A and B complement are also independent events. Perfect. So I hope this step is absolutely clear, right? So we've done the first part. The second is very similar, very similar. The only difference here is that now we are working with the B side, right? So now you can actually pause the video, answer this question, and then look into my suggestions, right? So again, we have two events, A and B, right? So we'll just make the same diagram as we did last time, But here the concentration is on this part, B part, right? So these are the events A and B. We are given A and B are independent. That really means that probability of A and B intersection is probability of A times probability of B. We need to prove that probability of A complement B is equals to probability of A complement times probability of B, right? Now, probability of A complement B is what? So if you look at the Venn diagram, you can clearly identify that it is this area. Perfect. So this area represents A not A complement of A intersection B. And here, like last time, we have a common area which is A intersection B. Now, how can you write B as? B is combination of both of these, right? So we can write A complement B plus intersection of A and B is actually equal to B, right? Now we can get to the probability part. So probability of A complement B. So steps now are exactly same as we did last time. Is it okay? So we could say plus probability of A intersection B. Last time I skipped this step, right? So we can write probability of A complement B is equal to probability of B take away probability of A intersection B, right? Which is probability of B take away probability of A times probability of B. You can take probability of B common, right? I mean 1 minus probability of A, which is equals to probability of B times probability of complement of A. That is what was required. So we again proved that probability of A complement intersection with B is equals to probability of A complement times probability of B, and therefore they are independent events. Therefore A dash or complement and B are independent events. Perfect. We'll take examples based on this. Now as the last part, I'd like you to pause the video and show that not A and not B are also independent events. So this is the last part. We'll again do the same sketch over which we had been working. So let me sketch it here this time. So we are looking for the two events A and B, which are given to us as independent events. So A and B are independent events. Let's say this is event A, this is event B. In that case, the center portion is A intersection B, right? Since A and B are independent, probability of A intersection B is equals to probability of A times probability of B. Absolutely clear. We want to show that A prime or not A and B are also independent. That is, we have to show that the probability of not A intersection not B is probability of not A times probability of not B, right? That is to prove. Now from this particular diagram, which area represents not A and not B? Well, the area which is not A and not B. So if you see outside the red area is this box here, right? Outside B is also the same thing. So this area here, let me just shade it now. Outside area, do you see that? Is this area here is not A intersection not B. Correct? How do we represent that? So I could say not A not B is if you see the union of these two, not the union of this. So we could say it is not the union of B, A and B. So that is the trick. So you could say not A intersection not B is actually not of union of A and B, right? Everything outside both A and B, that's what it means. So probability for A not A not B is equals to probability of A union B not. Perfect. Now that means I could write this as 1 minus probability of A union B. Correct? Complement 1 minus. That is how we should be doing. And now, what is probability of A union B? Well, so it is 1 minus, let me write in brackets, probability of A plus probability of B minus, because that has been counted twice, probability of A intersection B, right? Which is 1 minus probability of A plus probability of B minus. These two are independent events, and therefore it is probability of A times probability of B. Correct? Let's open the bracket. We get 1 minus probability of A, and let's keep them here, minus. Within brackets, let me take probability of B common. So probability of B common, we get 1 minus probability of A. Correct? Now, 1 minus probability of A is common in these two factors, correct? This and this, we have a common factor here. Do you see that? Therefore, we could write this as 1 minus probability of A, and here 1 is common, minus probability of B. Now that is complement, right? So we get probability of A prime or not A times probability of B prime or not B. Do you get it, right? So we have shown that the probability of not A intersection not B is product of probabilities of not A and not B, and therefore these two are independent events, right? So that is how we can actually show that if A and B are independent events, then these combinations not A, B, both not, are all independent events. So I hope the concept is absolutely clear. Now we'll take up a few questions based on these concepts. Feel free to write your comments and share your views, and if you like and subscribe to my videos, that'll be great. Thank you and all the best.